Welcome, folks. Today's lesson is going to be another lesson on stereochemistry. So far this unit, we've talked about how to identify the stereocenters of molecules. We've talked about how to assign priority to the groups surrounding those stereocenters and using those priorities to determine the configuration of a stereocenter. We've talked about different kinds of isomers, like constitutional and stereoisomers, and how to tell the difference between them. We have talked about different kinds of stereoisomers, like enantiomers and diastereomers and epimers. In today's lesson, we're going to learn about Fischer projections, which are really important in biology. We'll talk more about what a Fischer projection is later in the lesson. My learning objectives for you are that you will be able to convert between between a Lewis or skeletal structure of a molecule and the Fischer projection, and that you'll be able to use the Fischer projection of a molecule to draw the Fischer projection of a stereoisomer, so specifically an enantiomer, diastereomer, or epimer. Okay, so this is going to be our warm-up. Here I've drawn two molecules. See if you can identify the stereocenters of these molecules. So go ahead and pause the video for just 1 second and see if you can identify which of those carbons are stereocarbons. Okay, hopefully you paused the video and identified which carbons are stereocarbons, and hopefully you are able to determine that these 7 carbons were stereocarbons. We can tell these ones are stereocarbons because if you look at each one of those carbons, they have a different group. Or I should say, for each one of those carbons, they have 4 different groups attached to them. All right, the molecules in warm-up 1 have the exact same chemical formula, so they're both C6H12O6, and that means that they're isomers. So now for my second warm-up, I want you to tell me what kind of isomers are they, and how can you tell that they are that kind of isomer? So again, pause the video, go back and look at those 2 structures, and see if you can determine what kind of isomers they are. Okay, so hopefully you paused the video and took a look at those 2 chemical structures, and hopefully you were able to identify what kind of relationship they had between them. These are constitutional isomers, and we can tell because the carbonyl is not in the same position. So in the molecule on the left, the carbonyl is on carbon 1, so that makes that carbonyl an aldehyde. And on the molecule on the right, the carbonyl is on the second carbon, which is a secondary carbon, and that makes that makes that carbonyl a ketone rather than an aldehyde. Okay, and so next we're going to talk a little bit about those 2 molecules from warm-ups 1 and 2. And those molecules are glucose and fructose. Those are the names. You might have heard those names before. And that's because those glucose and fructose are 2 really common sugars, and they happen to be both 6-carbon sugars. And they happen to both be very important in biology. Now, sugars contain hydroxyl groups and a carbonyl carbon, and glucose is considered an aldose. That's what type of sugar it is. And that's because its carbonyl carbon is an aldehyde, right? So it's an aldose because the carbonyl carbon is an aldehyde. Similarly, fructose is considered a ketose because its carbonyl carbon is a ketone. All right, warm up 3. Determine whether each stereocenter of glucose is in an R or an S configuration. Okay, so now I've taken that molecule from warm up 1 and I've given each of the carbons, for each of those stereocenters, I said whether the bonds were pointed up or down, and this should let you determine. This should let you determine the configuration of each of those stereocenters. So take a minute and try and do that. Try to figure out whether each stereocenter is either R or S. Okay, so hopefully that's enough time. Let's go through these one by one. We'll start with the stereocenter at the top. And we're going to look at the 4 groups surrounding it. Now, recall that to assign priority, the first thing that you look at is the atoms that are immediately attached to the carbon. And you're going to determine whether those, you're going to determine the atomic number of those atoms, and the higher the atomic number, the higher the priority. So oxygen has to be priority 1 because it has the highest atomic number, and hydrogen has to be priority 4 because it has the lowest atomic number. So now it comes down to those 2 carbons. They have the same atomic number, so we look at the atoms that are attached to those carbons. The atom with the highest atomic number attached to each of those carbons is the oxygen. But one of those carbons is single bonded to an oxygen, and the other carbon is double bonded to an oxygen. And a double bonded oxygen will have higher priority than a single bonded oxygen. And so for that reason, that top carbon is carbon 2, and the bottom carbon is carbon 3. And so then if we draw the direction around atoms 1, 2, and 3 of the rotation from 1 to 2 to 3, we can see that our arrow is going counterclockwise. But since our highest priority group is pointed downwards, that essentially means that we're looking at this molecule from the bottom. And so normally for counterclockwise, we would give that configuration S. But since our highest priority group is pointed downwards and we're looking at it from the bottom, we're going to give that carbon configuration R. Okay, let's continue on to the next carbon. And so we can see that that carbon's actually attached to the same 4 atoms, 1 oxygen, 1 hydrogen, and 2 carbons. So again, oxygen's going to be priority 1 because it has the highest atomic number, and hydrogen's going to be priority 4 because it has the lowest atomic number. And the carbons, since they have the same atomic number, we have to look at what they're attached to. Well, those carbons are both attached to 1 hydroxyl group, 1 hydrogen, and 1 other carbon. So then what we actually need to do is continue down the chain and see which of those carbons that they're attached to has higher priority. And again, the carbon at the top is double bonded to an oxygen, whereas the carbon one down on the chain is only single bonded to an oxygen. So again, for that reason, the top carbon is going to have priority, and the bottom carbon will be priority 3. Let's draw our arrow. This is clockwise. But again, our highest priority group is pointed downwards. So normally when we see clockwise, we would expect the configuration to be R. But since our highest priority group is pointed downwards, we're essentially looking at this molecule from the bottom, which means that the configuration is actually S. Okay, let's move on to carbon 3. We've got our 3 groups. Oxygen is 1 again, hydrogen is 4 again. If we compare our carbons, one of those carbons is attached, Again, both of those carbons are kind of the same. They're both attached to a hydroxyl group, a hydrogen, and another carbon. So we have to go one up and one down on the chain. So if we go one up from that carbon is secondary, right? It's attached to another carbon. But if we go one down, that carbon is primary. And they're both attached to a hydroxyl group and a hydrogen. So the difference is the carbon at the very bottom is attached to 2 hydrogens, but the carbon when we go one up on the chain is attached to a hydroxyl group, a hydrogen, and another carbon. So again, the higher up carbon must be the higher priority, and the lower carbon is going to be our priority 3. And so then when we draw our arrow, we can see that that is going counterclockwise. So we would expect this to be S, but again, our priority 1 group is pointed downwards, so this is really configuration R. Okay, so RSR. Finally, we'll look at this group on the bottom. This one's probably one of the easier ones to assign priority. So oxygen is 1, hydrogen is 2. We look at the carbon on top, it's attached to a hydroxyl, a hydrogen, and another carbon. But if we look at the carbon on bottom, it's attached to a hydroxyl and 2 hydrogens. Well, since carbon has a higher priority than hydrogen, this must be priority 2 and this must be priority 3. And then if we draw our arrow, it's going like this in the clockwise direction. Our highest priority group is pointed upwards in this case, so we don't have to flip the configuration. It should really just stay as an R because it's going clockwise. Okay, so these stereocarbons are R, S, R, and R configurations. Okay, next we're going to learn about a tool in biochemistry known as the Fischer projection. And Fischer projections are a very useful way to represent biological structures. Oftentimes they're used for sugars and their derivatives, which is what we're going to do today. You can also see them used in amino acids and a variety of other structures. We're just going to talk about sugars today. And what the Fischer projection does is it makes it easy to determine the stereochemistry of each of the stereocenters. This was, I'm assuming a lot of you found this warm-up a little bit difficult to assign priority for each of those stereocenters. It's going to be a lot easier with the Fischer projection. The Fischer projection for a sugar is drawn by placing the carbonyl carbon, or the carbon that's closest to the carbonyl carbon, on the top. And then a line is drawn downwards from the carbonyl carbon with some intersecting horizontal lines to represent the stereocenters in the sugar. All right, to draw the Fischer projection for a sugar, you first consider the stereochemistry for the stereocarbon that is furthest away from the carbonyl. Right, so we're going to look kind of at the bottom for that bottommost stereocenter. If that carbon has an R configuration, then the OH group is drawn to the right of the intersection, and the sugar is said to have D configuration. If the carbon has an S configuration, then the OH group is drawn to the left of the intersection, and that sugar can be said to have an L configuration. The remaining stereocenters can be drawn in a similar manner, with the OH group going to the right if that carbon has an R configuration, and the OH group going to the left if that carbon has an S configuration. All right, so let's go through an example. So here's glucose again, and just to remind you of how we labeled those stereocenters, they went R, S, R, and R. We're going to start with the aldehyde at the top, and then we'll draw a line going straight down. And then we'll draw an intersecting line for each one of those stereocenters. And then the carbon at the bottom is not a stereocenter, so we'll kind of just list the formula for that carbon. It's a carbon attached to two hydrogens and a hydroxyl group. Okay, and then we're going to start with that carbon at the bottom, which is R, and so we'll draw our OH group going to the right. And again, that tells us that our molecule is in a D configuration. That one's also going to the right because this carbon is R. The next carbon is S, so the OH group is going to the left. And then the top carbon is R, and so the OH group is going to the right. And so this is D-glucose, and again, it's a D configuration because this bottommost stereocenter is pointed to the right. And then we can number those carbons, 1, 2, 3, 4, 5, 6. And that'll be important because when you get to your assignment, we're going to take D-glucose, and I'm going to ask you some questions like, draw the diastereomer that differs at carbon 2, right? So you're going to have to know to flip the configuration on carbon 2. Or I might ask you to draw the diastereomer that differs at carbons 3 and 4. So you're going to have to flip the configuration at carbons 3 and 4. We'll go through an example of how to do that in just a second here. First, I want to do a little bit of review from our previous lesson on stereochemistry. Remember that there's two main types of stereoisomers. So those are enantiomers and diastereomers. Enantiomers are non-superimposable mirror images of one another. So I know that's can be kind of a lot as far as the definition goes. Remember what that means though. Like if you think about your hands are mirror images of one another, more or less. But they're non-superimposable. Right? So if you put one hand on top of the other, well, then your pinkies are where your thumbs are, and so they don't actually line up on each other. You can't superimpose them. They're not the same thing when you put them on top of one another. Perhaps a more useful way to define a pair of enantiomers is two stereoisomers that differ in their configuration at every stereocenter, though not all pairs of enantiomers have stereocenters, right? So this is useful when you're talking about stereoisomers with stereocenters, but you could have stereoisomers and enantiomers that don't have any stereocenters, and those are kind of actually those end up being kind of those end up being examples that are kind of like out there a little bit. You're not going to encounter examples like that a lot, but it is worth knowing that they exist. Okay, next let's talk about diastereomers. Diastereomers are also non-superimposable stereoisomers. However, they are not mirror images of one another. Perhaps a more useful way to define a pair of diastereomers is two stereoisomers that differ in their configuration in at least one but not all stereocenters. So some of their stereocenters are different, but not all of them, if that makes sense. And then you could also think of cis and trans conformations as being diastereomers as well. So if you think about molecules with double bonds or ring structures, those could also be considered diastereomers. But we're thinking about stereocenters today. That's why I'm giving you these kind of simplified definitions for stereocenters. A subset of diastereomers is the group of isomers known as epimers. So first of all, what's a subset? A lot of you know that I also teach math. So a set is sort of like a list of things. In math, we say that a set is a list of mathematical objects. And so a subset is a list that's contained in a larger list. So like if you think about like the list of all rectangles, well, a square is a rectangle. So the list of all squares would be a subset of the list of all rectangles. You could think of it with numbers too. So if you think about integers, right? Remember, an integer is like a whole number, right? Like +2 or +8 or -5 or 0. And then rational numbers, those are numbers that can be represented as a fraction of two integers. Well, all integers are rational. So what we could say is that the set of all integers is a subset of the set of rational numbers. You could also do this with something like less abstract, like say, for example, all lions are types of cats. So the set of all lions is a subset of the set of all cats. Okay, I don't want to spend any more time on this for now. Epimers are diastereomers that differ in their configuration at exactly one stereocenter. So remember, we said that diastereomers differ in their configuration in at least one, but not all stereocenters. Epimers differ in their configuration at exactly one stereocenter. So no more, no less. Example 2, let's draw the Fischer projection for the enantiomer of D-glucose. So here's D-glucose. Okay, so we're going to draw the enantiomer. So remember, the enantiomer differs in stereochemistry at every single stereocenter. So what that means is every single one of these OH groups is going to be going in the other direction. So if we look, that top OH group is going to the right. So we're going to draw the top OH group in our enantiomer going to the left. Same thing, the OH group on carbon 3 is going to the left. We draw it going to the right in the enantiomer. Right? All of them are just going in the exact opposite direction. Okay, and then this molecule, because it's the enantiomer of D-glucose, we actually just call that L-glucose. Right? The enantiomers of sugars, they actually have the same name. We just change the configuration from D to L, or L to D if you're doing the enantiomer of an L sugar. This is going to be important for the assignment that you do today, because I am actually going to have you name the sugars. So when you draw the enantiomer of a sugar, they have the same name. You just change the configuration from D to L or vice versa. All right, let's go through one more example. Now we're going to draw the Fischer projection for the epimer of D-glucose at carbon 4. So here's D-glucose. I'm going to draw my my skeleton for my Fischer projection. Now, for carbons 2, 3, and 5, they're going in the same direction. It's only at carbon 4 that the OH group gets switched. So that's this carbon right here, this fourth one down. It switches so that that OH group is pointed to the left now instead of to the right. And this molecule also has a name. I wouldn't expect you to know this. On your assignment, I will kind of give you the names of all of the different sugars, and so then once you draw it, you'll just have to match it up to the list of structures that I have down below. But this actually ends up being D-galactose, is the name of this sugar. Okay. So now let's talk about the assignment. So on today's assignment, you will begin with the Fischer projection for D-glucose. So I've shown you that in the slides today, but you'll also have it on your assignment. And you will draw the diastereomers for carbon positions 2, 3, and 4. Now when I say you're going to draw the diastereomers, you're going to draw every possible combination of diastereomers. So you'll draw when it's flipped at carbon 2, when it's flipped at carbon 3, when it's flipped at carbon 4, when it's flipped at carbons 2 and 3, 2 and 4, 3 and 4, and then the diastereomer when it's flipped at all three of those positions. And then for each of those Fischer projections that you draw, you're going to draw the enantiomer that goes with it. And then again, I give you a resource to help you name those structures. So you'll name them. And then finally, I'm going to have you identify which of those structures is an epimer of D-glucose. So if you don't remember what an epimer is, go back in the notes here and see if you can figure it out from the definition that I had you write down. Then you're going to choose one of those epimers of glucose, and you're going to draw its skeletal or Lewis structure with wedges and dashes. Okay, so let's just take a look at the assignment real quick here, and then I'll let you get started on that. So again, here's the Lewis structure for D-glucose, and here's the Fischer projection that goes with it. And then I also gave you the Fischer projection for its enantiomer, L-glucose. And remember, every one of those is just going in the opposite direction. And then if you look up here, this tells you which diastereomer of D-glucose I want you to draw. So here it differs at carbon 2 only, differs at carbon 3 only. For this one, differs at carbon 4 only. We did that in the assignment. So it's the diastereomer where it differs only at carbon 4. And that one we said was called D-galactose. When it comes to naming these things, I have the names of all of the, these are called aldohexoses. Aldo because they have an aldehyde, and hexose because they have 6 carbons. I gave you the names of all of the D-aldohexoses. So you can use that to name your structures once you draw them. You just match them up with the diagram down here. And then remember that once you have the name, when you're naming the enantiomer, right, you just change the configuration designation from D to L. Okay, and then once you have once you have all your structures, you're going to tell me which ones in the table are epimers of D-glucose. I'm going to give you a hint. Glucose has 4 stereocenters, so there should be 4 epimers. So you tell me which of those 4 structures are epimers of D-glucose. And then you're going to pick one of those epimers of D-glucose, and you're going to draw either the Lewis or the skeletal structure. And that Lewis and or skeletal structure should have wedges or dashes into it that correspond with the configurations from the Fischer projection. And you'll do that down below here. Okay, let me know if you have any questions.